Thanks everyone for attending this talk. Today we are delighted to have Edith Cohen from Google Research and Tel Aviv University giving a talk on robustness to adaptive inputs and a case study of CountSketch. So this is the second talk in a series of 4 on adaptive and adversarial streaming, and so I'm really happy that Edith accepted to give the second talk. Edith received a PhD in computer science from Stanford in '91, and then has an extensive experience working for industry and done fantastic work in graph algorithm sketching, sampling, machine learning, you name it. She has many prizes, including being a fellow of the ACM, 2007 Bennett Prize from the IEEE CountSketch, and an impressive number of patents and publications. So I'm really happy we get to hear her giving a talk today, and I'm not going to use your time more. Edith, floor is yours.
Thank you. So thanks to Barna, Clement, and Venkata for inviting me, and for Clement for hosting the talk. So I'll talk about robustness to adaptive inputs and our study of CountSketch. Let's see. Okay, so I'll go back and forth between a background and our specific setup of CountSketch. So the work on CountSketch is joint with Xin Lyu from Berkeley student, with Jelani Nelson, with Tamas Sarlos, Moshe Shechner, who is a student in Tel Aviv, and Uri Stemmer. Okay. So so what are so there was the previous talk in the series, but what are adaptive versus oblivious inputs? So we have an algorithm with internal randomness, and the algorithm interacts with an adversary or just another algorithm. So it takes queries and it gives answers. And basically, we want the answers to be correct, to remain correct for all the inputs. So in the non-adaptive setting, the input sequence does not depend on the outputs. In the adaptive setting, we allow inputs to depend on prior outputs. So this is the difference. And when do adaptive settings arise? They can arise naturally when the systems have feedback. And sometimes we also consider adversarial situations where there is an adversary, that the goal of the adversary is to construct an input or an input sequence on which our algorithm fails, meaning one of the responses is incorrect. So, okay, so type of settings where this happens. So we have a data structure that is some representation of the data set, and it's maintained under updates. The inputs are updates to the data set, and what we maintain is some representation. And then the outputs for the queries are computed over the representation. So this happens with the dynamic graph algorithms. Say the updates are edge additions and deletions, and we answer queries over the representation for efficiency. And another setup is streaming algorithms. So we have some vector, and we have we maintain some summary structure, and this is done for space efficiency. So In adaptive settings, the updates may depend on responses from queries from prior states. So adaptivity can arise there. And another type of settings is that we have some model that maps inputs to some representation. It could be embeddings, it could be a sample, it could be a sketch. And then whatever output is computed over this representation. So this happens with adaptive data analysis, say over a sample, and then we keep answering questions depending that we keep asking more questions that may depend on prior responses. Sometimes optimization has feedback loops and so on. Okay, so when can input adaptivity be an issue? So if the algorithm is deterministic, or if it uses like fresh randomness per output, then we don't worry about it, because when even if you know prior outputs, it doesn't really change anything. So there is an issue when outputs may depend and leak information on the internal randomness of the algorithm. And in this case, adaptive settings are kind of harder to analyze. So we want to show basically something like for all input sequences, the probability over the internal randomness that we choose for the algorithm that the answers are correct is larger than something. So in the non-adaptive case, a typical analysis might look like that. We look at each input, and then we compute the probability that the output is incorrect, given all prior inputs or the current input, depending on the setup. So we bound that, and then we can just apply a union bound over all the steps. So intuitively, in this setting, we would need many, many non-adaptive inputs until we stumble upon something that is the incorrect output. But in an adaptive setting, outputs may leak information on the internal randomness, which means that the inputs depend on the answers and then depend on that randomness, and this analysis kind of breaks. So because the probability that an answer is incorrect provided all the answers before no longer is equal just to the probability that in one step the answer is incorrect, and then that kind of potentially can lead us to, or an adversary to quickly zoom on an input that has an incorrect output. So that's why it's kind of much harder to analyze. Okay, so now a little bit on CountSketch. CountSketch, I look at CountSketch was introduced by Cherry, Karchen, and Farah in 2002. Before that, variations of it was introduced as feature hashing for a different set of applications. So basically, it's a dimensionality reduction tool. You have vectors in a large dimension, and their sketch is a vector in a much smaller dimension. And this is done by a matrix that is randomized. There is some internal randomness. And that internal randomness, it could be like hash functions. It specifies the measurement vectors. And the sketch is basically the inner product of these measurement vectors with our input. And it has a much smaller dimension. Okay, so this is very nice for applications. So it was introduced in the context of streaming applications. It's also good for distributed applications because it's very easy. Like if you just get updates to the input, it's very easy to maintain the sketch of the vector. And what you gain by that is a small storage or communication. Also CountSketch sometimes is used as a component of a larger system or a pipeline, for example, in the entry to a neural network as a compression module. So you have very large sparse inputs, you kind of do some dimensionality reduction to make things more efficient. Okay, so what does this sketch give you? So okay, so you reduce the dimension by a lot, but you can still get a lot of information out. It supports recovery of the L2 heavy hitters of V, which I'll define soon. And it also, more in its application for feature hashing, it also supports approximating the inner products of two vectors from their sketches. A variation of it is basically, it can be saw this way, is the AMS sketch and also the Johnson-Linderson transform, and then it allows recovery of L2 norms and distances. So it's a very useful kind of dimensionality reduction. So recovery in the terminology that we use is done by applying some estimator to the sketch. So it's basically applying some algorithms that take the information from the sketch and gives you some estimate of what you want, a list of heavy hitters, inner product, and so on. So, okay, so in our application, I'll focus more on the L2 heavy hitters property. So if we have a vector, L2 heavy hitters are entries. So we have, with respect to some epsilon, are entries that have at least epsilon of the L2 mass, in a sense, of the square of the L2 norm. So it's entries that their square is at least the square of the L2, epsilon times the square of the L2 norm. And sometimes we look at just the tail of the vectors, which is the vector with the largest entries removed. Okay, so for example, in this vector, the heavy hitters with respect to epsilon equals third are the two red entries. Okay, so the L2 heavy hitter problem is to return a set of entries that would have size at most 1 over epsilon that includes all the heavy hitters. There are at most 1 over epsilon heavy hitters. So this should be sufficient. Okay, and CountSketch does this pretty nicely. If you use dimension that is proportional to 1 over epsilon times log n over delta, the median estimator allows you to recover approximate values for all the entries that are within epsilon times the squared norm, and with the okay, so and then with when it's non-adaptive inputs, you just increase the dimension by log times, and you get correct heavy hitters for all these inputs. So basically, it allows you to answer correctly exponentially many queries, kind of. The query you think of, you get a vector and you report the heavy hitters from the sketch in the sketch size, okay, when in the non-adaptive setting. Okay. So what do we do with adaptive input? So the first strategy that we would try is maybe it's a randomized algorithm, maybe try to find a different algorithm, because because adaptive input don't degrade performance when they are deterministic or when there is a fresh randomness used per output. So this sometimes works, but with CountSketch and all the variants, these are essentially the only tools we know of, the only tools we have to give small space sketches that support recovery of L2 heavy hitters and noise. And also there are results that show that there are no deterministic sketches, but basically we don't know of anything else that can work. So, and this is in contrast for L1 heavy hitters, where there are deterministic and fully robust sketches. So there are randomized sketches, but in this case there are deterministic sketches that work. So, so we have a solution. But here we're kind of stuck with CountSketch and its variations. Okay, so what are the general tools we have out there? So the non-robust baseline that we want to avoid is basically use fresh randomness per query. So the sketch size would scale up with the number of inputs we want to answer in a robust manner, and that's bad. So David Woodruff in the last talk in the series talked about a technique called sketch switching. So there, basically, the idea is to use fresh randomness, refresh the randomness, meaning basically use a different sketch, or only when the output changes. So in our case, it would change in the reported set of heavy hitters, but still the size of the sketches that you need scales linearly with the number of changes. What comes to our help here, it's a general tool, is a robustness tool, differential privacy. This is a very powerful and very beautiful connection between that gives us also a very nice technique to get to avoid this linear dependence. Okay, so I'll give some, I'll survey this a little bit. So okay, so now we're talking about a little bit of a different problem, statistical queries over samples. So suppose we have a distribution, and then we have our inputs here are predicates, and the outputs that we want is basically the expectation of that predicate over the distribution. But we want to do it over a sample. So in this case, we can think of our internal randomness as defining the set of IID samples. And for the query, we give an approximate answer, which is basically the empirical average of the predicate over our samples. Okay, so in the non-adaptive case, we all know this is trivial with Hofding. a sample of basically if our accuracy and the confidence are constant, it's basically a constant size sample, and we get good accuracy with the specified confidence. And then if we want to answer R different, we have R different predicates, the sample size that we need increases only logarithmically in that size. And this is in the non-adaptive setting. So basically, we can answer with these samples a number of queries. We can accurate for a number of predicates that is exponential in the sample size. Okay, so what's happening in the adaptive setting? So if we insist on reporting the exact empirical averages, if that's our estimator, then we can do better than a number of queries that scales linearly in the sample size. So we can always use fresh sample per query, so we can always get that dependence. And it's very easy to see that, if we ask the queries strategically, we can identify, we can think of our samples as basically spelled, written as in the binary form, and basically just ask queries on the bits in the sample, and then using tilde or the queries, maybe deal of the queries, we can find all the prefixes that cover the sample very well, but then there will be a tiny fraction of the whole distribution, so we can construct a predicate where the sample says 1, but the actual expectation is close to 0. So, okay, but what we used here is that the exact empirical averages are reported. So now a really beautiful result is connection between robustness and differential privacy made by Dwork et al. And Ban et al. And basically they say, okay, we allow the predicates to depend on the sample. Okay, so in the non-adaptive case, it doesn't depend, but now we allow it to depend on the sample, but in a way that preserves the privacy of the sample. So we can't report exact counts. It has to be noised up a little bit. And if we can do that, if the choice of the predicate preserves the privacy of the sample, then the empirical average kind of still is guaranteed to generalize. We can't do what we did before. Meaning that the empirical average is close enough to the actual expectation. So this is below is the statement of the theorem. It's basically showing that the privacy parameters kind of match the sample size, the regular sample size parameters. Okay, kind of. Okay. So now we have a very easy way to make this statistical query interaction private. We basically just add noise to the reported empirical averages. And what's really the workhorse here in the analysis is the differential privacy advanced composition. So the privacy cost of our queries, we're asking many queries, one after the other. So the privacy cost adds up, but it scales up just like square root of R. So So our privacy noise, so if our privacy noise, additive privacy noise, scales like square root of R, and our sample size is D, suppose we want some fixed error like 0.1, then we can see that we can answer about these square queries using these samples. So this all comes out from DP advanced composition. It just falls out. And another thing that DP gives us for free here is that all these predicates adaptively depend on each other, but the composition just applies in this case. So it's very nice. And there is also, yeah.
Oh, no, I was going to ask if that was tight. So, okay, this is tight. Okay.
Okay, and there is also a matching lower bound, and that's using fingerprinting codes by Hart and Neumann, and Steinke and Neumann improved it. And then any correct algorithm basically can be made to reveal the sample under that, after that many queries. So it's kind of tight in some worst case sense. Okay, so this is the key idea, and another very important idea is kind of using it for a more general randomized algorithm. This is by Hasidim and Kaplan, Mansour, Matthias and Stemmer. So then basically they take this tool, but they say instead of applying it to samples, they apply it to internal randomness of multiple algorithms. So basically, suppose you have a non-adaptive algorithm to solve a problem. You can make an adaptive version out of it using kind of the following scheme. You instantiate DIID copies of the non-adaptive randomized algorithm. Now, for each input, you kind of update, you run it on all the copies. And when you want to report the answer, you take some differentially private aggregate of all the answers. And then, and then you output that. And so basically you use privacy to protect the internal randomness of the algorithm. So it's very, very cool. So basically it kind of gives you the same thing. You can answer these square queries with this method using D copies of the algorithm. So this was used in different settings. Initially, it was introduced in the context of streaming algorithm, but of course, this also works with dynamic graph algorithms. The only difference with dynamic is that you keep the data, and then when you run out of space, when you run out of robustness, you just can create a refresh. And with streaming, you do everything in parallel. But it was also used for machine unlearning. This is when you want to kind of delete examples from your model. Another very cool thing is that because you use kind of privacy, you can use all the machinery that comes with differential privacy. So, so basically, if you have queries or responses when there are no changes, you can use techniques like sparse vector technique where they don't incur any privacy cost. So you basically get for free this what you might have worked harder to get with this sketch switching technique, right? Just with privacy, you just don't pay for outputs where the when the output doesn't change. because you just apply sparse vector. Okay. So now, okay, I guess that's just said. So now back to CountSketch. Okay, so we can apply that to CountSketch, but maybe we can think of applying it in a little bit better way. The wrapper takes the whole algorithm as a black box, but maybe tailored approaches can do a little bit better. There are also questions on the lower bounds. The lower bounds we've seen before were used for statistical queries, use the fingerprinting codes. So can robustness to adaptive input be an issue for our algorithm in practice? Is it with natural inputs? Is it with weaker adaptivity? Or maybe even the algorithm is robust as is. So we'll try to see what we can get on these two fronts. So, okay, so I'll give some review of CountSketch. How does it work? So the parameter D is basically the number of linear measurements. And there is a parameter B that is scales like 1 over epsilon, which basically is the accuracy of the heavy hitters, the fraction of the norm we want to get. So the sketch kind of is designed like D over B sets of B measurements each. So, and then, so the purple set is a set of, is one set of 3 measurements. So basically every entry of, so it's defined by 2 hash functions. One maps every entry in the vector to one of these 3 buckets randomly. And the other assigns a random +1 or -1 sign to every entry of the vector. And then this set of buckets, the projections are as follows. So you look at all the entries that fall in the bucket, and you multiply it by the sign, and then you add it up. So for example, the entries -2, 5, and -1, the values map into this middle bucket. So here the -2 is multiplied by -1, so it's 2. 5 by -1, so we get -3, and then the -1 is multiplied by 1, so it becomes -4. So this is the projection. Okay. So this is how CountSketch works. So these different sets of measurements are kind of independent of each other. So what's happening here? So if we have only like 3 heavy hitters, or order 3 heavy hitters, okay, then it's likely that they will each map to its own separate bucket. They'll be alone in the buckets, and then all the other keys that map into that buckets would be in the tail keys, the much smaller keys. And since these entries are large, basically they'll dominate the bucket. The others, the contribution of all the others together would look like the L2 squared norm of the tail divided by the number of buckets. Okay, so this is how CountSketch works, basically. Okay, so how do we get estimate on the value of the key? We look at all the buckets that one in each set that the key maps to, and then we look basically at the value in this bucket, and we multiply it by the sign of the key in that bucket. So we get the number of sets kind of estimates for the value of each key, and the classic estimator takes the median of these values. Okay, so this is and then with the median estimators, we get the performance that we saw before, that all the entries are estimated within epsilon times the norm. Okay, so this is the performance we saw before. Okay, so now how can we improve over that? How can we improve can we obtain with for adaptive inputs? Okay, so the first thing we can do is apply the wrapper as is. So we apply the wrapper to full IID count sketches. And then for every input, we always report like 1/epsilon heavy keys. So basically, we get like R/epsilon different queries. And then the number of sketches, IID sketches that we need to answer them is the square root of that. So this is the number of measurements that we need. So, so there is a dependent, there is 1.5, there is 1/epsilon to the 1.5 dependence. So this is if we apply the wrapper as is. So now we can look at CountSketch and we can try to do better. We can reduce the privacy unit from being a whole sketch that we try to protect to just one set of buckets. But that doesn't give us that much, maybe just a log factor. So what we managed to do is reduce the privacy unit to just a single bucket. But a difficulty was that the CountSketch buckets were not IID. They are treated as samples, but they are not IID in this case. So we had to change CountSketch to an IID version where everything in the same set are kind of independent. And that that's where we could gain. We gain the factor of square root of epsilon. Okay, so other components of what we needed to make that work is a different estimator. It's no longer the median estimator that kind of evaluates a predicate for each key according to the alignment of the sign of the bucket with the sign of the key. And also some careful privacy accounting that we only use the relevant buckets to charge the relevant buckets for each key. So we took that wrapper, but then we adapted it to a particular to our particular application of the CountSketch. So we could do a little bit better. So this is the version of CountSketch where the different buckets are independent, basically. Instead of hashing things to a partition, we just randomly choose assign each item to each entry to each bucket. Okay, so now I'll move to lower bound. Yeah.
If I have a question in the previous slide, what is B like?
Oh, B is like the width of the sketch. So CountSketch is kind of two parameters.
Right,
so
right.
If we want heavy hitters that are epsilon of the L2 norm, then B is 1/epsilon, about order of 1/epsilon. Sorry about that. Or usually if you talk about K heavy hitters, B is order K. The K largest, or it's not largest, but 1/K of the norm, yeah, or epsilon of the norm.
And how does the transformation make it a IID? Like, is there an intuition behind that?
Yes, so with CountSketch, you use like a hash function that kind of maps, it kind of does a partition. Each key out of the N is mapped to exactly one bucket in the set, okay? But now we basically just say each key has probability 1 over b of mapping to each bucket.
Okay.
So there is a little bit of a loss because we don't get exact number of rows estimates for each key. It can vary, but then it gives us the IID property that we need for the kind of that privacy tool analysis to go through. And it's actually an interesting question if that tool can be kind of extended in ways that we don't have to do this acrobatics and we can just apply directly to CountSketch.
Right.
But we still don't know the answers for that. Yeah.
Thank you.
Okay, so another question, which is actually what the question that we started with, is whether the median estimator, maybe it already is robust and with to adaptive inputs. So the answer was negative to our surprise initially. So we could construct an attack of that shows it's really non-robust. It's basically almost as bad as using a fresh sketch for query. And the attack kind of has a particularly simple form. So okay, so here you assume that you basically return some number of K prime keys that have the largest estimate. So you use a CountSketch with the median estimator. You get you basically get estimates for the values of all keys, and then you just return the K prime keys that have largest estimates. So the way you attack that, you construct the vectors as follows. So you use a K prime plus 1 designated keys. K prime minus 1 of them are very large, are pretty large. And the other two have the same kind of borderline magnitude. And then there is kind of a tail of, almost everything is 0, but there is kind of a tail of size T of plus minus 1 random entries, okay? So what's happening here is that so the K prime largest estimate would always include the K prime minus 1 heaviest keys and one of the two borderline keys, key 1 and key 2. And then the attack is very simple. It goes as follows. It's basically it does this query with a random tail. And now if the first key is reported as a heavy hitter, it adds that random tail part positively to some vector. And if the other key is reported, it adds it negatively. So basically, we just collect kind of a sum of these tails. And then what we can see is that kind of it biases buckets that where the first key participates towards the sign of the first key on these buckets. And it goes the other way for the buckets where the second key participates in. It kind of biases it away from the sign, meaning that sum of tails that we collect is more likely to be negatively correlated with the sign of the second key on the bucket that it participates in, and more likely to be correlated positively with the sign of the first key. So, and then, and the final adversarial vector that we have would have a 0 on the keys 1, 2, and would be heavy on the heavy keys, and basically it would report keys 1 and 2 as having the largest magnitude, okay? Because one would accumulate high positive bias and the other would accumulate one negative bias, huge negative bias. Why this is happening? So basically, bias. The idea is the very high level idea is that the bias accumulates linearly when we keep adding the vectors, and the norm, it's like the noise, it grows like the square root. So if we do it enough time, these very slight biases of the tails that kind of distinguish between keys 1 and 2, which one looks slightly larger, it kind of accumulates. So if we look at basically the set of estimates for key 1, so basically, and just the contribution of the noise to them, of the random noise, it's like basically random coins, positive or negative. And then, but there are slightly more ones in the direction that you want, about square root of the number. It's like a random walk kind of bias. And then if you do the computation, you see that basically you get this this dependence of that the number of rounds is like you get this linear dependence. Okay. So we actually simulated this attack, and it even works with pretty small constants. It doesn't really take that many attack vectors to build a really bad input for this sketch. So here we look at the bias to noise ratio. So basically for R equals 1, which means the bias is about the magnitude of the heavy hitter you want to look at, it's basically a very small constant. Okay, so what are the takeaways from this attack? It's basically minimalistic, it's very simple. It doesn't take much from the output. Basically, all you need to know if key number 1 is reported as a heavy hitter or not. It's basically just 1 bit output. But another thing here is that basically all the inputs we use for the attack, they are not adaptive in a sense. Only the final constructed output is adversarial. Only the adversarial final output depends on the prior inputs. And also that the vectors used in the attack are kind of very natural. It's one heavy key with a little bit of a random noise. So it's almost like such attack vectors, maybe you can just construct them by observing the system kind of a normal operation. So it shows some basic susceptibility of this type of sketches. So the attack, we talked about a non-streaming setting where you kind of take an input vector, you look at its sketch, and then you report the heavy hitters, but you can just basically do the same in a streaming setting. Because you just need to actually report just changes. So you can just emulate that in a streaming setting. But what we attacked here is basically a very specific estimator, the median estimator. And the next question, which is basically in a paper that is now in submission, it's another result. So what if you don't restrict the estimator? So we show that any correct heavy hitter estimator for CountSketch can be attacked with a quadratic number of inputs. So the median estimator, it suffices to attack it with a linear number of inputs, but any estimator can be attacked with a quadratic number of inputs, any correct estimator. And this also holds for inner product estimator and also holds for norm estimators for AMS sketch. But there is a little caveat here that basically what the attack means here, the product of the attack, so all we guarantee is that the sketch is completely out of distribution. That it doesn't behave, it doesn't have the normal properties that you would expect from the sketch of the inputs, like the expected the values of the buckets will be completely off from that. But we don't actually show that any estimator would fail on that sketch. But it's still, it means that many systems that kind of train with this type of sketch built in the pipeline, they would probably fail. And this also is basically the same form of vector. So it's a very weak adaptive setting where only the final input may depend on the prior, only the final adversarial input may depend on prior outputs. So yeah, and the attack vectors are also just a heavy key and random noise. So what's the notion of correct heavy hitter estimator for the attack? So it's very weak. We just say it cannot report a zero value key as a heavy hitter, and it must report a heavy key. And basically this is the attack, just a heavy key and random noisy tail. And what we do here is that we select the weight of the heavy key uniformly at random over the decision boundary between what we can't report and what we must report. And when a key is reported, we add the tail to the final adversarial input positively and otherwise negatively. But we have the quadratic bound here because basically the correlation is weaker between what is reported and the actual bias of the tail. So the high-level ideas in the analysis is that no matter what correct estimator is used, it can change between inputs, it can be adaptive. So no matter what's happening, a tail that is biased towards the heavy key is always slightly, with the way we choose the weight, is slightly more likely to result in the key being reported as heavy, right? So there is this slight correlation no matter what that we explore. And again, it's the same basic idea. The bias adds up linearly, the noise grows with square root. So we add up these very, very slight advantages, and then we get an input on which the sketch is completely off. So summary, okay, so this is okay, lower bound, the classic estimator of CountSketch, which we shown it's not robust, can be attacked with a linear number of inputs. Any estimator can be attacked with a quadratic number of inputs. And then there is a kind of a matching upper bound. There are still some more interesting questions, but for example, for the AMS sketch, it looks like the weaker attack on some high accuracy regime is not tight. And also it might be possible to construct such attacks on a more general kind of dimensionality reduction sketches. So we basically use the randomness of the input for the attack. So and that Yes, so it can be maybe extended to larger classes of sketches, I suspect. So anyway, so I think the time is almost out. Sorry. Yeah, so thank you for listening.
Thanks a lot. Okay, so if there's any question from the audience, please feel free to unmute yourself or just ask in the chat, and I'll convey the question. So I had one small question. So your lower bound seems pretty depressing, right? Like it attacks CountSketch, and also it's not even like it requires a lot of adaptivity. It's not a very contrived instance. Is there any way to bypass it, making some reasonable assumption?
We hoped so, but it's like, yeah, that's our feeling too. It was pretty depressing. But one thing is that, okay, so where you get hits are on inputs that are on the decision boundary. When your inputs are far from the decision boundary, you don't pay for them. And basically, the very careful kind of privacy accounting techniques can kind of capture that. Because if you're nearly deterministic, if you're very, very heavy, or if you're not heavy at all, then I mean, you don't reveal anything on the randomness. Yeah, so maybe it's like D square, but you don't pay if there are, in some scenarios, when there are no changes in the output, or if you're very far from the decision boundary. So the actual situation might be a little bit better.
Thanks. Yeah, there's a question about whether the recording will be made available, and yes, the recording will be made available on the website. Okay, I had another question actually, which was, so one way you mentioned at the beginning was, oh, let's just use fresh randomness from the start, but I mean, of course, that scales with the number of things you answer. Is there any way that like some de-randomization can help a little bit there, saying, oh, we don't actually need fully fresh randomness, just a little bit, using some, I don't know, like random walks techniques to de-randomize with like a small seed? Does that give anything, or is it just already not useful because it scales linearly with the stream?
You mean, I mean, in some other settings, in dynamic graph algorithms, I always sometimes they run into these issues, and then they manage to design a deterministic component that kind of gets robustness to adaptive inputs. Here, so how would you? You're asking for a CountSketch specifically?
Oh, no, like in general, another baseline, which would be, instead of using fully fresh randomness, we can just have like a very small number of random seeds that allow us to pretend we have a lot of randomness, because maybe our sketch only needed, I don't know, pairwise randomness, or it's good enough. And so we get also some savings in the space because of that. Is that, or is it just like optimizing constants at that point?
I don't know. No, I don't even think it's optimizing constants. So here it's like, okay, so in this analysis, it doesn't matter if you defend a huge string of full randomness, or you just defend the hash function, the random hash function for each bucket. That would not make a difference. Yeah, you kind of want to make it more deterministic, but yeah, I see what you're saying. Yeah, I don't see how you can get, but maybe there is some way. I don't know. That's a good question.
Thanks. All right. So if there's no other question, maybe we can just stop the recording, and if there are people who want to ask offline, they can do that now. So thanks again, Edith, for the great talk. And
Glad to see you. Yeah.
thank
Thank
you.
you, Edith. Yeah, very nice talk.
Thank you. Okay.